Welcome back. In 23-4, we're going to be talking about the alveoli. And by the time we've really reached the respiratory bronchioles and the alveoli, air has been cleaned and moistened. And so by the time we get to this point, we should really only be focused on diffusing and exchanging O2 for CO2. So if for whatever reason there is debris here, really delicate surfaces of the alveoli are going to probably get damaged. And once those alveoli are damaged, they will not be able to be regenerated or reused. So instead, the lungs will have to redivert where air is going. So if it's going to alveoli A or A, B, and C, and all of a sudden A doesn't work, it might have to diverge its route from A and instead go from ABC to BCD, essentially. The end of the alveolar duct is when we'll start seeing alveolar sacs, and even smaller than that, we'll finally have those individual alveoli. So speaking of debris, let's talk about smoking again. So smoking tobacco, if we were to spread out all of our alveoli in one person, in one healthy, normal adult person, and we spread them out and laid them flat, they would actually cover half of a tennis court in terms of surface area. And how much do you think smoking on a pretty regular basis would actually decrease that surface area by? By about 75%. So that half tennis court actually then becomes, 1/4 of that 1/2. So what is that, 1/8? So you only have 1/8 of a tennis court left for use to actually get air in and get air out, which obviously has a lot of detrimental effects. So let's talk about the alveoli in particular. On the right, we have a cartoonistic depiction of what's going on. The alveoli themselves are made out of simple squamous epithelium, which makes sense because we want them to be really thin and not stacked so that we can have really easy gas diffusion, so we can move from a high to a low concentration. We have pneumocytes type 1, which are making the majority of this simple squamous epithelium. And then we also have pneumocyte cells type 2 surrounding it. Do you need to know the difference between 1 and 2? Yes. The difference is 1 are just kind of the structural support of the alveoli, and type 2 produce something called surfactant, which is really important. Surfactant is going to be really helpful for us in terms of compliance for moving the alveoli and letting them expand and collapse. So we can picture each alveoli as kind of my analogy that I always like to use is a hair tie or a rubber band, right? A hair tie is only good if it isn't loose or really bad at bouncing back and not so good at holding on to the hair if it's stretched out really far, right? Same thing with a rubber band, right? No one can do anything with a really loose rubber band, and no one can do anything with a really tight rubber band either. You kind of have to have this right size for the right shape of whatever it is that you're trying to hold together. So that's essentially kind of what surfactant is doing for us. Surfactant is that rubber band. It's going to help open the alveoli, but not open them so much that they burst or tear. And it's also going to help them not, whenever they close, not collapse in on themselves, which makes a lot of sense. If you think about blowing up a balloon, right, the first couple breaths into the balloon, like breath 1 and breath 2, are really difficult, right? You have to put a lot of force in, you have to put a lot of air before you actually finally start to get the balloon to expand. And once you finally get it to expand, then it's really easy to get more air in and then finally tie it off. The same thing can be thought of with the alveoli. If you have really floppy alveoli and they're just squished and they've never been opened, or maybe maybe previously they've been opened, but they're entirely flat, it's going to take a lot of pressure, a lot of effort in order to actually get that air into that alveoli. And so in order to prevent that from happening every single time, surfactant is actually going to help keep it open ever so slightly so that it doesn't take as much effort in order for that air to seamlessly go into the alveoli during that inhalation. So surfactant is actually made out of oil, mucus, and water, essentially, and it just covers a very thin layer of itself. It just covers the alveoli on the inside. And like I said, I just went through the entire function of the surfactant. One thing before we leave this slide, I also want to mention that sandwiched in between the type 1 and type 2 cells, we also have some macrophages present, just to collect information on if there's an infection present. Okay, so moving back to the surfactant story, here's a picture on the left about kind of the pros and cons of having surfactant present. So let's pay attention to the picture on the right first, or in the middle here. So with surfactant, whenever air comes in, air can kind of somewhat equally enter into both alveoli. It doesn't just get directed into one. Versus without surfactant, we might be stuck with just being able to put air into one alveolus. And the same analogy can be applied here for if you were blowing up one balloon versus two balloons. If you put both balloons not in your mouth, but you're trying to blow up two balloons at the same time versus one balloon, right? Two balloons is much more difficult than one balloon. But imagine if one balloon was slightly more pumped up than the other balloon, then it's still going to be a little easier to pump up both balloons, and air is probably going to go into both balloons than it would be if they were both just flat. And so that's what that picture on the left is trying to depict. On the right, we're introducing the blood-air barrier. So we have on the top half of the screen, we have the capillary, the alveolar capillary, the pulmonary capillary. And that'll be one cell layer thick because endothelium lining is one cell layer thick, and capillaries are also one cell layer thick because they're meant for diffusion. We can't see this with the naked eye, remember that. And then we have a basement membrane that's connecting the capillary to the mainly pneumocyte type 1 type cells of the alveoli. And the idea is to have air come from, not air, but an exchange of O2 and CO2 across this barrier. So O2 is very, for lack of a better word, it's promiscuous. It likes to go wherever it wants to go, and we don't know if it's coming or if it's going, and we don't know how long it's going to stick around for, and it usually doesn't stick around for a long time. Versus CO2 likes to hang out for a long time. It likes to stick around, and it's actually pretty hard to get rid of. So this makes it a little complicated because if we're trying to get oxygen to the tissues and we're trying to get out CO2 from the tissues and breathe it out, this makes this process really essential that we make sure that it's as easy as possible to get oxygen from the alveolus into the pulmonary capillary in order for oxygen to have any chance of actually getting to the tissues. And likewise, in the other direction, once we finally get CO2 into the bloodstream and back into its gas form, then it'll move from a high concentration within the pulmonary capillary to a low concentration within the alveolus so that we can breathe it out. Like I said, it's three layers thick. Let's talk about what happens if bad news bears happens at the blood-air barrier. So let's talk about pneumonia. If we have pneumonia, this is an infection within the lung, which is going to produce a lot of inflammation. With a lot of inflammation, we know that we slow blood down, we bring a lot of fluid to the area, we increase temperature, we have a recruitment of a bunch of white blood cells, and because of this, there is so much pressure of the amount of fluid buildup in this area that some of it can actually leak from the interstitial space or from within the pulmonary capillary itself into the alveolus. And if it goes into the alveolus, then now we have a problem with that mixing with the surfactant, which isn't good, so surfactant can't work as well. And it's also taking up space. And if it's taking up space, that means we can't put as much O2 in as we normally would be able to, because O2 isn't just going to hang out in this extra fluid. It doesn't want to, it doesn't need to, it's just hanging around. And then let's imagine if that fluid continues to build up, and finally it starts closing off alveoli entirely, and then leaking backwards into the respiratory bronchioles. And if the respiratory bronchioles are irritated, now they're wrapped around in smooth muscle. That smooth muscle might constrict to help try to kind of like save one part of the lobe of the lung so that it doesn't spread. And now we have a completely useless portion of the lung, so we can't breathe at all. This is how pneumonia works, essentially. It's a really common secondary infection from those who are immune compromised for whatever other previous reason. So we see pneumonia a lot of times in the hospital. See you in the next one.